Because it's a risk that Tony may have to rush off to the safe room if the sound goes off, the way we're going to do it is we're going to show a video we made yesterday of Tony's talk. But Tony is around, he is here. Say hello to everybody, Tony.
Okay, hello everybody. I hope you can hear me. Thank you.
And hopefully he'll be still around and not cowering in
Right.
space.
So I think so as well.
We'll answer your questions at the end of the meeting. If not, well, I have to try and do it myself. I do know quite a lot about the subject, so hopefully, one way or the other, we can manage. Hello, Tony. Good to see you, and I hope you're bearing up. Well, could you now please give us your talk on the shades of industrial hydrogen, grey, blue, green? Over to you, Tony.
Okay, Peter, thank you and the RSC Historical Group for inviting me to give this talk. I hope everybody can see the screen clearly. Hydrogen is a small molecule with a major presence. Once released from water and hydrocarbons, it is an industrially important molecule. The methods for achieving this release on a large scale are the theme of my talk today. In an earlier Zoom presentation, I highlighted hydrogen's role in the manufacture of synthetic ammonia, perhaps its most important use. I will return to this shortly. Hydrogen must be used with great caution. Dramatic examples of this are the LZ-129 Hindenburg disaster in May 1937, resulting from its ignition, probably caused by an electric spark, and the rupture of high-pressure industrial plant as the result of hydrogen's decarburization of steel. In this case, in 1930, an ammonia reactor or converter has fractured as a result of embrittlement. There are several methods that have been used to commercially produce hydrogen, of which those highlighted here receive the most attention. Historically, the earliest large-scale use was in heating and lighting with water gas, a mixture of hydrogen and carbon monoxide mainly produced from coal or coke when treated with steam. This was attempted several times during the 19th century. The water gas and other hydrogen-generating processes inspired Jules Verne to predict a future when energy needs would be satisfied by hydrogen as well as oxygen. The water gas processes were perfected around 1890. Unlike lighting with coal gas, water gas did not require extensive infrastructure for gas storage and distribution. Until the 1890s, the preparation of hydrogen by electrolysis of water was confined to the demonstration bench. Electrolytic processes relied on cheap electricity, which was invariably from hydroelectric power as generated at Niagara Falls. Hydrogen was a byproduct of the electrolysis of aqueous sodium chloride, used in the production of alkali, though this source was not used widely in manufacture until the first decade of the 20th century. Then hydrogen was used in hydrogenation of fats and in the manufacture of hydrogen chloride. This is a Hooker electrochemical setup of around 1910. Water gas was soon preferred as a source of hydrogen in the chemical industry. This began with the large-scale production of hydrogen for the synthetic ammonia process, that is the Haber-Bosch process. Hydrogen is combined with nitrogen under brute force conditions at a high pressure and an elevated temperature in the presence of a catalyst. In this apparatus based on Fritz Haber's work, the catalyst is in the chamber at the left-hand corner, which is called the converter. The hydrogen had to be extremely pure. Production of water gas from blowing steam on red-hot coke released carbon monoxide and hydrogen. This was followed by several steps, including reacting the water gas with steam to give a mixture of carbon dioxide and, at the same time, more hydrogen. This is the water gas. This is the process whereby the water gas was formed. This shift reaction has continued in use in many cases where fossil fuels are used to produce hydrogen. You can see the equation is very simple: carbon monoxide reacting with water to give carbon dioxide and more hydrogen, and the steam treatment of water releases carbon dioxide, which is released to the atmosphere. One of the problems we'll come back to shortly. The process was introduced on a large scale by BASF's Carl Bosch at Ludwigshafen, just north of Ludwigshafen, at the Oppau works of BASF. Until recently, the carbon dioxide was invariably released to the atmosphere. However, especially from the 1950s, in certain manufacturing plants, carbon dioxide was captured for use in the synthesis of the important fertilizer urea, and in other cases, it was applied to the food and beverage industries. The synthetic ammonia and petrochemical industries are today the major users of the shift reaction. The hydrogen-carbon monoxide or syngas reaction was used in the manufacture of methanol by a similar process. Reactions of synthesis gas, carbon monoxide and hydrogen, are associated with the work of Franz Fischer and Hans Trops, who in the mid-1920s in Germany catalytically produced hydrocarbons from the syngas mixture. Their gas source was coal or coke, and the method was placed on an industrial footing in Germany in 1936. Their high-octane gasoline produced by this reaction was incredibly important for the Luftwaffe during the Second World War. There was a great deal of interest in this reaction in the second half of the 1940s, especially in the United States, for production of synthetic gasoline and other products. George Cloud was another pioneer in the ammonia industry. He had many problems setting up his industrial process because the converters kept exploding. However, he was a pioneer also of producing hydrogen from coke oven gas. This was very important, especially in Europe, although it was not taken up in the United States. Friedrich Bergius is another pioneer. He developed coal hydrogenation in the early 1900s, and with Carl Bosch shared the Nobel Prize in 1931 for their hydrogenation work. And this Nobel Prize was, in fact, the first Nobel Prize given for inventions in industrial chemistry. Well, now we come on to ICI Billingham, which copied the BASF process for making ammonia. At ICI, the Bergius process for converting coal via hydrogenation into gasoline was adopted on quite a large scale. And here we see some of the reactors used in the reaction. What is important today is that the off gases from coal hydrogenation, low boiling hydrocarbons, were reformed. They were reformed in such a way that they produce carbon monoxide and hydrogen. This led to the development of a method for producing hydrogen from natural gas. It could not be taken up in the UK because there was no natural gas. But in the Second World War, this process was extremely important in Canada and US. ICI assisted North American engineers to develop the process, and there were at least 8 factories built to use natural gas as a source of ammonia. Well, the process involved two stages involving primary and secondary furnaces. What is important about this image is that most of the reaction, or the most important part of all the process, took place here in the preparation of hydrogen. The manufacture of ammonia itself was just a small part of, took up just a small part of the site. And there were two types of, there were two reformers, the primary reformer and the secondary reformer. These furnaces were extremely important in the production of hydrogen. The secondary furnaces included incorporation of nitrogen from the atmosphere in the production of a gas suitable for the ammonia process. The hydrogen had to be extremely pure. There were very many stages used in its purification, as suggested by the previous slide, including the use of ethanolamine in the removal of final traces of the carbon monoxide, which was extremely toxic for the reaction. ICI in the 1950s developed a process for making hydrogen from naphtha. This was an extremely important process for very many years until it was replaced by natural gas in the UK. ICI also developed technologies for catalysts, which were extremely important worldwide in the production of synthesis gas, that is, in the production of hydrogen, as well as in the ammonia synthesis. We go back to this diagram of the preparation of ammonia from natural gas, simply to emphasize that from the shift reaction, which takes place around here, carbon dioxide was allowed to escape to the atmosphere, but it also produced, as I pointed out earlier, more hydrogen. And then all this mixture was processed through the various steps to produce a mixture mixed with nitrogen that was converted into ammonia. I want to emphasize for a moment the importance of hydrogen in the ammonia process. Carl Bosch, in his Nobel Prize lecture, stated that the procurement of hydrogen is the largest item in the prime cost of conversion of the ready-made gas mixture into ammonia. This is an extremely important point about the manufacture of ammonia. A similar statement was made by Charles O. Brown of the Atmospheric Nitrogen Corporation in the United States, who stated that the development and purification of the hydrogen is still the outstanding feature of cost and extensiveness of plant equipment. And here's an example of one of the reformers constructed by the engineering contractor Foster Wheeler, very large concern with international connections. And you can see here this extremely large reformer. This process of reforming was carried out on a vast scale. Well, all these processes required compression of the gases. Here we see reciprocating compressors around 1930s used in typical synthetic ammonia plants. The capacities of these compressors was limited. Hence, there were several trains all lined up together, each one provided with compressed gases from a separate compressor. Well, the importance of this was that another engineering contractor, M.W. Kellogg, undertook semi-commercial studies on pressure reforming of natural gas. What happened in this case, the natural gas coming out of the well was under a relatively high pressure. As a result of using the gas already under high pressure, the cost of the compression required for the ammonia synthesis was reduced by 25 to 35%. Kellogg, in the mid-1960s, introduced centrifugal compressors and developed a process for making ammonia, which produced tripled the amount of material that could be obtained from a single converter. And I should also point out that a lot of the work on the primary reformer was done by ICI even in the 1950s, but Kellogg took the process much further, integrated its experience in petroleum refining to develop this very important process. Well, let's change from natural gas and coal processes to another pioneer, Luigi Casali, who used his process for making ammonia, the hydrogen from water. The outstanding feature of Luigi Casali's process was that the reaction was undertaken at 800 atmospheres. This meant that the product was liquid ammonia. Here we see Casali's process for producing liquid ammonia. Here is a compressor. Here is the reactor, and the liquids were collected by just cooling. No refrigeration was required. Quite a remarkable situation. And as I just pointed out, Casali promoted production of hydrogen by electrolysis. This was carried out on a large scale, for example, in Japan and in Italy. Well, to summarize so far, pure hydrogen was made available from coal, the BASF process, electrolysis, the Casali process, coke ovens as the result of work of Fowler and Cloud in the mid-20s, from natural gas developed in the 1940s in the United States, but based on work started by ICI in the 1930s, and finally naphtha, another ICI process developed from the 1950s. Well, now we come up closer to the present, to the oil crises of the 1970s. There were great concerns in the US over shortage of natural gas, which was a premium fuel for domestic heating and lighting, and therefore there were considerations of other sources of hydrogen for making ammonia. This included a return to coal-based processes based on synthesis gas. In the UK, North Sea gas was available from the early 70s, which made a tremendous difference to the economy of the country. In the meantime, the ICI naphtha process was taken up in India and China and elsewhere and used until the earliest 20th century. Now we come to the present. The designations given to shades of hydrogen identify the production process and the impact of the process on the environment. The most important are grey, blue, and green hydrogen. Other names that are used include black hydrogen, which refers to coal-based processes. Grey hydrogen processes, generally from natural gas, allow the escape into the environment of carbon dioxide. Blue hydrogen processes, generally again from natural gas, involve the capture of and storage of carbon dioxide. Green hydrogen is associated, by contrast, with processes that do not produce carbon dioxide. So green processes are very much required in reducing the carbon footprint. Green hydrogen means a return to electrolysis. Here, solar energy is a strong candidate for production of a sustainable source of electricity. When hydrogen is burnt, the product is just water vapor. Therefore, vehicles using hydrogen as fuel rather than fossil fuels do not emit greenhouse gases. At the beginning of the 20th century, there was a great deal of optimism that we would soon have an economy based on green hydrogen. There has been a great deal of literature since then, most especially, if anybody is interested, Jeremy Rifkin's The Hydrogen Economy, borrowing from the World Wide Web, whereby information is transferred by the internet. Jeremy Rifkin, subtitle was The Creation of the Worldwide Energy Web and the Redistribution of Power on Earth. This is a book certainly worth reading, but nothing or very little of what Rifkin predicted has actually come to pass, and he has been criticized by many people. However, the transition from fossil fuels to renewables with clean energy and reduction in greenhouse gas emissions has to confront the present commitment to and security in fossil fuels. This is its major problem. the companies have invested so much in fossil fuels, and particularly natural gas processes, that it's very difficult to wean them away towards clean energy processes. However, government subsidies are encouraging research into more efficient electrolyzers. These very modern electrolyzers include catalysts to encourage the breakdown of water into hydrogen and oxygen. Green hydrogen is already bringing about transition in some sectors. And I'd like to emphasize the use of green hydrogen in railway transportation. In China, green hydrogen locomotives are already at work, and this is a German rail car that declares that it's a world premier train using green hydrogen. The use of green hydrogen as a fuel for road transportation and domestic heating, however, remains a contentious issue. This is not the case for production of ammonia and steel. In the US, green hydrogen has already been used in the production of ammonia. And in Germany, green hydrogen has been used in the production of steel. These are on a small scale, but they do certainly prove the viability of green hydrogen in overcoming much of the pollution problems from ammonia and steel manufacture. The synthetic ammonia, as a consequence, has begun to migrate to locations rich in hydro, solar, and wind power, including the Middle East and Australia. However, there is another potentially important source: extraction of geologically preformed abiotic hydrogen, or white hydrogen, generally deep underground, found deep underground as a result of the reaction between hydrothermal water and iron-containing rocks. There is also hydrogen as a co-product of the electrolytic chloroalkali cells. This is another important source of hydrogen still in use today. What is important, however, is the fact that ammonia is an important energy carrier for hydrogen. Hydrogen, as I pointed out in the middle early on, is quite dangerous and has to be treated with great care. Liquid ammonia, however, is easy to ship and much safer. The hydrogen is released by cracking the ammonia at the destination at a high temperature with a noble metal catalyst. This is effectively reversing the Haber process and offers a method for using ammonia as a fuel. This is a very important consideration today. In the early 1930s, the research arm of the Ammonia Casale company modified a motor car engine to accept liquid ammonia as a fuel. In the engine, the ammonia was cracked to give hydrogen. While it was not entirely successful, perhaps it offers inspiration for modern-day inventors. And here is a plan of Ammonia Casale's motor car setup. The liquid ammonia is here, produced in that form by the ammonia converters, and the engine is here. Well, all I want to say now, after this brief introduction, is thank you for everybody for looking and listening. I hope you've learned something a little bit about hydrogen. It's an extremely important element, has been used industrially since the early part of the 20th century on a very large scale, and has an even greater future ahead, subject to another of constraints such as overcoming the near total commitment to fossil fuels in its production. Thank you.
What car manufacturers are the furthest ahead with hydrogen vehicles? That's not really strictly speaking what you were talking about. You were talking more about using ammonia for hydrogen. Okay, Jeff Seaman pops in here. Jeff says, The chemistry underlying the subject is fascinating in saying the phase diagrams and analysis. Also, under certain conditions, ammonia can lead to spectacular explosions to rather those of converse hydrogen, so perhaps not quite as safe as you said, Tony. Anyone want to say anything about all that, Tony? Use of hydrogen,
Okay.
safety of hydrogen, safety of ammonia.
Can everybody hear me?
I think so.
Can you hear me, Peter?
Yes, yes, people are saying yes, yes. I think if they
Oh,
can
very good.
somewhere.
Okay. In terms of car manufacturers, I do watch the news on this topic, and there are firms moving in and out all the time. And if anybody wants to drop me an email, I can do a quick check. But there's a lot of controversy, and of course, competition with battery vehicles. And the big problem with hydrogen-powered cars is the infrastructure to provide the hydrogen in the first place, which is very much a negative aspect. And many municipalities have introduced hydrogen power buses, which are now parked because of the lack of infrastructure for obtaining hydrogen. So I can't give you a lot of information on that topic, but I'll be pleased to look it up if anybody wants to send me an email. Regarding Jeff's comment, yes, very fascinating chemistry here. Very simple equations, very small molecules, but absolutely fascinating mechanistic and the kinetic aspects. I couldn't agree more. Incidentally, if anybody has any questions after the lecture, please get in touch with you either directly or via Peter by email, and I'll do my absolute best to fill you in.
Okay, I'll pass on any messages that you'll get, Tony. Two things I was going to mention. Firstly, hydrogen in motor cars, or automobiles if you're American. They don't actually burn the hydrogen directly, I don't think, do they? They use fuel cells, which in fact was first invented by Chief Justice Grove, in fact, if I remember correctly.
Sorry, not very clear, Peter. But yeah, I heard you mention fuel
Yeah, I was
cells. Yeah,
making the point that hydrogen vehicles, so-called hydrogen vehicles, don't actually burn the hydrogen in the sense of burning it in oxygen. They use fuel cells, is that correct?
That's correct, yes.
So, okay, so they're not burning it in the sense where one burns petrol or gasoline.
Right, exactly. That would be very dangerous, I think.
And in fact, it's the same as they use on spacecraft, I think. I think spacecraft use fuel cells as well. Is that right, Tony? Tony, can you hear me?
Can you repeat, please?
I was talking about spacecraft, but they
Oh,
use
spacecraft. Yeah, there have
they
been
use fuel
discussions, just
cells in
like
spacecraft.
there have been discussions about hydrogen, just as there have been discussions about nuclear-powered spacecraft in the past. In fact, there has even been discussion about using nuclear power around 1980 in the production of hydrogen. But how far hydrogen has gone in propelling spacecraft, I'm afraid I'm not an expert. Again, I'm happy to look it up if anybody's interested.
Yes, in fact, you raised an interesting point. Well, indirectly, you've raised an interesting point, which perhaps could have been made in the talk, but never mind. And that is fusion power would, of course, transform the picture completely, wouldn't it? If we had
Right,
cheap fusion powered electricity, we could just use electrolysis without a worry in the world.
right.
In
Yeah, I
fact,
think that,
In fact, you could even use it, and I was thinking about this when they were talking about the water on the BBC News just before this talk. But if you were burning hydrogen, and I mean burning hydrogen in the literal sense rather than in the sort of fuel cell sense, although Verso may not make any difference actually. But if you had lots and lots of cheap electrically generated hydrogen and you burnt it, you would then get lots of pure water as well. So, in fact, it would be a way, in fact, would it not, of desalination, because presumably seawater is rather good for electrolysis because it's got a salt in it to increase the current, just
mhm.
as the furic acid in the Voltman voltameter. So if you use electrolyzed seawater, you get hydrogen, which you would then burn, and then you get pure water afterwards.
But it's rather like decomposing ammonia to get hydrogen.
Yeah.
Very similar situation, and that hydrogen is very pure.
But but to pick up a point we talked about yesterday when we were making the recording, um, why are people so down on the use of hydrogen for domestic use to replace natural gas? Because it seems an obvious thing to use hydrogen instead of natural gas. It's almost going back to coal gas without the carbon monoxide. And yet, if you read about it in the papers and whatever, everybody poo-hoos it.
I think people are still frightened about leakages from infrastructure and potential for explosion. I'm not sure that these are valid excuses, but this is in the popular media. This is the sort of question that comes up.
Yeah, but I think it seems a great pity to me because instead of being heat pumped, which are technologically fantastic but practically useless, we could just be switching our natural gas for hydrogen. It seems a no-brainer to me, but every time it comes up, if somebody comes along and says, "Oh no, no, you're thinking illegal thoughts. You mustn't think about that. We must go down the heat pump route."
Good point.
I personally just don't understand it because it's the same as coal gas, effectively. In fact, in the days of coal gas, they actually boosted coal gas, didn't they, by adding extra hydrogen to it? That's why water gas was
Great,
for.
great, right.
So, anyway, I'm probably boring everybody here. Is there
No, on
anything
the
you got? And
contrary.
I would still have you in person before you go rushing off to the safe room, which I hope will not be necessary ever again. Uh, but is there anything else you want to say, Tony?
Yeah,
Anything?
I just saw a note on the screen about the fact that the production of hydrogen is extremely energy intensive, which is absolutely correct, and which is why water, solar, and wind power are considered as very viable resources for production of the energy required to produce the hydrogen. But nevertheless, it's something that's not always taken into account.
Okay, well, good point. Well, I hope you all did enjoy it, and thank you, Tony, for giving that talk. And next month we've got another regular of ours, Alan Dronfield, and he's going to repeat the talk he gave at our meeting on chemistry, history, and medicine about TB. It's not just about TB drugs, although TB drugs are an important part of that, but generally about the history of TB and the significance of chemistry in that topic. So please come along next month when it'll probably be even hotter than it is today. It is very warm in Tony, by the way. And I hope to see you all again. Please, let's meet up again next month. Okay, bye for now.